Welcome to today's Explainer. I gotta tell you, I am incredibly pumped about this one because we're digging into a cosmic mystery of literally epic proportions. We're gonna look at exactly what happens to a planet when its host star dies. It's this wild, almost post-apocalyptic scenario playing out across our galaxy. And thanks to some brand new data, we're finally piecing together the clues of a planet that didn't just survive the apocalypse, but somehow snagged a second lease on life.
To really wrap your head around the scale of this mystery, I want you to imagine our own solar system, right? But about 5 billion years from now, our sun has completely burned through its nuclear fuel. In its violent death throes, it swells up into this massive red giant, completely swallowing and vaporizing the inner planets. So say goodbye to Mercury and Venus. Earth's fate is totally borderline. But for the rest of the solar system, gas giants like Jupiter and Saturn, it leaves a massive question mark. Can a planet actually survive the violent, explosive death of its very own star?
The transformation is honestly staggering. Think about a healthy main sequence star, like our current sun. It's massive, humming along on nuclear fusion, keeping all its planets in tight, stable orbits. But then, fast forward to after that red giant phase ends. The star sheds all its outer layers, and the core just collapses into a white dwarf. We're talking about an object shrinking from something massive down to roughly the size of Earth. And because this dead stellar core has lost so much of its original mass, its gravitational grip on any surviving outer planets weakens dramatically. The whole system becomes destabilized and orbits start shifting everywhere.
All right, let's jump right into Section 1, Meet Survivor Planet WD-1856b. It's time to introduce the star witness of our cosmic detective story, a world that somehow made it through the fire.
Meet the survivor, WD-1856b. Sitting about 82 light-years away from us, this thing is a Jupiter-sized gas giant. But the orbital stats are what really jump out at you. It is locked in an extremely close orbit around its dead star, just 0.26 astronomical units away. That is a tiny fraction of the distance between Earth and our sun. To put that into perspective, this planet completes a full orbit, an entire year on this world, in just 1.4 Earth days.
Oh my God! Wow!
But what's truly mind-bending here is the sheer scale of the system. We're so conditioned to think of stars as these massive objects, and planets as comparatively tiny specks, right? Well, in this case, the planet is actually 7 times larger than the stellar corpse it orbits. The host white dwarf is just about Earth-sized, while the planet is the size of Jupiter. It's this incredibly bizarre cosmic geometry where the planet absolutely dwarfs its own sun.
Which brings us to Section 2, a bizarre JWST discovery. To figure out how this giant ended up so close to a dead star, astronomers pulled out the heavy artillery. They aimed the James Webb Space Telescope, specifically its NIR-spec PRISM instrument, straight at this system, and they observed something completely unprecedented, a 56% transit depth. That is the highest transit depth of any known exoplanet. Think about that. Because the planet is so much larger than the star, it's literally blocking out more than half of the star's light during its brief 8-minute transit across the face of the white dwarf. When that data dropped, especially at the longer infrared wavelengths, the scientific community was just stunned. Dr. Ryan McDonald from the University of St. Andrews perfectly captured the mood in the room when he simply said, "Wow, what the heck is going on here?" The transmission spectrum they were looking at was completely unlike any other planet ever observed.
And here is the massive anomaly they stumbled on. This host star has been a cooling, dead white dwarf for 5.4 billion years. So, logically, a planet orbiting it should be absolutely freezing. Thermal models predicted an expected temperature of around negative 113 degrees Celsius. But JWST revealed that the actual temperature is a baking 126 degrees Celsius. It is mysteriously hot, and at first glance, that made zero sense. Digging deeper into the atmospheric data, JWST revealed a surprisingly complex world. We're looking at a deeply carbon-enriched atmosphere with about 7% methane and other hydrocarbons. There's also this optically thick cloud deck sitting deep in the atmosphere, meaning it's completely opaque to visible light. On top of that, the planet exhibits extreme metallicity. Basically, it has about 100 times the heavy elements of our own sun, which supercharges the production of aerosols and hazes. Honestly, chemically speaking, it looks a whole lot like the deep inner layers of our own Neptune. Now, if you're wondering, okay, but how sure are astronomers about these weird readings? Just look at these odds ratios. The odds of hydrocarbons like methane being present range from 167 to 1 up to over 5,000 to 1. The presence of aerosols, greater than 200,000 to 1. But the absolute kicker is the detection of night-side thermal emission, meaning heat radiating from the planet itself. That sits at an astronomical 2 billion to 1. That concept, night-side thermal emission, is so crucial here. The reason the transit looked shallower at those longer infrared wavelengths is because the planet itself is glowing with intense heat. The infrared light coming from the planet's own baking hot night side was literally diluting the starlight being blocked. This planet isn't just reflecting light, it's practically radiating its own heat out into the void of space. So, Section 3, Solving the Heating Mystery. Time for the deduction phase of our explainer. We've got a planet sitting at 126 degrees Celsius, orbiting a star that's been dead and cooling for over 5 billion years. Where in space did this immense heat actually come from? To figure that out, scientists first needed the planet's mass. Thankfully, the JWST data provided the first constrained mass for WD 856b, placing it somewhere between 4.3 and 10.9 times the mass of Jupiter.
Nice.
So we're dealing with a very heavy, massive gas giant. And knowing that mass is basically the skeleton key here, because it allows scientists to use thermal evolution models to calculate exactly how long it takes a massive planet like this to cool down after a major heating event. By running the clock backwards based on its mass and current temperature, they built a fascinating timeline. Step 1, the main sequence star dies. Step 2, the destructive red giant phase ends and the white dwarf is born. But step 3 is the twist. The data definitively shows that the planet got blasted with heat 3.0 to 5.5 billion years after the white dwarf formed, leading right up to our present-day observation. The logic here is absolutely crucial because it flips the whole narrative on its head. Since the reheating happened billions of years late, we can completely rule out the star's fiery explosion as the source of that 126-degree temperature. The planet wasn't just roasted by the red giant phase and stayed hot. No, something else entirely happened to it during those dark, cold billions of years that followed. Which brings us to our final act, Section 4, A Planet's Second Life. Let's uncover the true culprit behind this massive thermal anomaly. The winning theory is this chaotic process called high eccentricity migration. Remember earlier how we said a white dwarf has less gravitational pull, making the surviving solar system less tightly bound? Well, over billions of years, gravitational interactions with other surviving bodies in that system literally knocked WD 1856b out of its safe, distant orbit. It got pushed into this highly elliptical, wild oval-shaped trajectory. And here's exactly how that played out. First, the orbit becomes that extreme stretched-out oval. Second, this new path causes the planet to swing dangerously close to the white dwarf on every single pass. Third, every time it swings in close, the intense gravity of the dense white dwarf physically yanks and squeezes the giant planet. Fourth, all that physical squeezing creates immense internal tidal friction, literally warming the planet from the inside out, generating the massive heat that brought its temperature all the way up to 126 degrees Celsius. And finally, that continuous loss of energy acts like a brake, eventually rounding out the orbit into the tight 1.4-day circular path we see today. It generated its own heat through friction, effectively earning a second life. I honestly think this quote from Dr. Ryan McDonald beautifully sums up the incredible resilience of giant planets in these post-apocalyptic systems. He said, "Stellar death is not the end, it is a new chapter in the life of planets like Jupiter." Even after the host star completely dies, the dynamic, chaotic evolution of the system just keeps going. Which, of course, leaves us with a truly provocative question to chew on. If a gas giant can survive a stellar apocalypse, migrate inwards, and get a second heated life, could a rocky planet like Earth do exactly the same thing? Could we one day find a rocky world sitting right in the new, ultra-close habitable zone of a dead white dwarf, maybe even harboring new life long after its sun has died? It's an absolutely thrilling frontier for astronomy. If your mind was just blown a little bit today, hit that like button and subscribe. Stay curious, and I'll see you in the next video.